In this video, we'll continue our discussion of linear independence and how it connects to solving systems of linear equations, which will then build into differential equations later on in the course. The question I left you with last time was the largest possible number of linearly independent three-component vectors that one can have, and similar for n. So think about how this works. Well, how do we define if vectors are linearly independent? We put them as the columns of a matrix and row reduce. If we have three component vectors, for instance, we know that there will be three rows of matrix because every vector has three components. So we'll have, our vectors 1, 2, 1, 0, 2, 3, 5, 1, 8, minus 1, 2, minus 3, and so on. However many there are you think you can put there, we'll do that. And we row reduce. And we know there's three rows, and what's our criteria? Well, if we're going to have linear independence, every column must be a pivot column. So how many pivot columns can this matrix have? Well, a pivot column is determined by a column having in it the first non-zero entry of a given row in the row echelon form. So because there are only three rows in this matrix, I can only have a maximum of 3 pivot columns because each one must correspond to the first non-zero entry in a row, and there are only 3 rows. So what that means is that if I have any more than 3 columns here, or any more than 3 vectors, they must be linearly dependent. Because if there's more than 3, I will guaranteed have a non-pivot column. So for three component vectors, the largest possible number of linearly independent vectors is 3. Cool. And by the same logic, for n component vectors, I can have no more than n linearly independent vectors. So this here means something. I can never have more than n vectors of n components that are linearly independent. So what you want to look into now is what happens if you have that maximum number. So if I give you a collection of 3 vectors, each with 3 components, that are all as a set linearly independent, what happens? Well, it turns out this is where things get interesting. This is where we start tying everything back together. So let's assume that we have that. Let's assume that we have n component vectors. I have n of them, and they're linearly independent. And I give you some other random vector b. I will look at the possibility of choosing c1 through cn such that this all adds up to b, that c1, v1 plus c2, v2, and so on adds up to the vector b. What do we know here? Well, we know one thing in particular. We know that if b was 0, I can give you an answer. Because if b is 0, this is the exact same thing as the definition of linear independence. If this is the case, we know that the only way to solve this is picking all the c's equal to 0. Because of the definition of linear independence. Well, that's not much. But how did we get there? We got there via a row reduction approach. Right, we got there by putting the v1, v2, vn, at least theoretically, into columns, and then row reducing and seeing that in the resulting matrix, I had pivot columns in every column. And that's what forced all these c's to be 0 to make this work. So because we know these are independent, we know that if I row reduce, starting from the matrix with the v's as columns and a 0 on the right side, then if I row reduce that, what I will end up with is something that has 1s on the entire diagonal, 0s below it, and all 0s on the right side. The 0s on the right side don't change, and because these are independent, I know every column must be a pivot column. I'll end up with 1s on the diagonal, 0s all over on this side, and then on my right-hand side, all 0s. I don't know what's up top here, and I really don't care. It does not matter. The point is, this row reduction tells me that these are linearly independent because the last row tells me that Cn must be 0. The row before told me that Cn minus 1 has to be 0 and backtrack all the way up. Now, the row reduction process does not care about the right column of the matrix. So if I redo this row reduction process again, but instead of putting 0 on the right hand side, I put this vector b, I can do the exact same row reduction steps. The exact same way I got from the 0 case on the right to the same thing that I had up top, I can do the exact same steps again. And if I do that, I will get the same left-hand side, and on the right, I'll get some numbers. I don't know what they are, but they're going to be some numbers depending on the vector b. The operations don't care about what b is, but they will affect the values that are in that spot. So we'll do all these changes, we'll follow the steps through and do them that they're supposed to, and we get to here. What do I see from this? I say that I will have exactly one solution here. I can pick Cn to be this Bn star, and I can back solve all the way back up to solve for all the other Cs. So this will always have exactly one solution. It does not matter what b is. It doesn't matter if b is 0 or some other vector. I will always get exactly one answer here because the fact that I get one answer only depends on the vectors itself and not on the right-hand side be. If you think about some stuff from solving systems in general, we had this case of getting 0 or infinite solutions. That requires linear dependence, and then the value of b matters. But if we have independence, where we're going to get exactly one solution, it does not matter what b is. You always get exactly one solution every time. So if I have a set of linear independent vectors, and I have n of them for n component vectors, no matter what vector b I choose for the right-hand side, this system here, this equation, will always have exactly one solution in terms of the c's. There's exactly one way to write b as a linear combination of the v1 through vn. And this result is so important that we have a new definition based around it. This is how we define a basis for a vector space. So a basis is a collection of vectors v1 through vk. They're all vectors in the right vector space, so that they are both linearly independent, and for any other vector b in that vector space, I can pick coefficients c1 through ck such that there's a linear combination that adds up to give me b. So what have we learned? We've learned that if I have a collection of n linearly independent n component vectors, they automatically form a basis for all n component vectors. So another point that I'm not going to specifically prove out here, but you can think about why it might work, is that you also can't have less than n vectors and still get a basis. The reason for this is that if I have less than n vectors, I have too many rows for the columns that I have. And so if I row reduce, I'm going to end up with a pivot column landing in that B, that far right side column, and that means there's no solution. My last row will say 0, 0, 0, 0, something non-zero, and so that will give me no solution. And so there won't be a way to sort of cover everything or get to every vector, every possible B, if I have less than n vectors. So it has to be n. This n is called the dimension of the vector space. It is a common quantity in linear algebra. It's used a lot all over the place. And so you need n of them. And once you have n that are linearly independent, that's automatically a basis. So this idea of making sure we have enough vectors or enough solutions and being able to hit every possible vector B is reminiscent of things from second order equations, solving initial conditions. Maybe the fact that for repeated roots, we only had one solution that wasn't enough. We had to find something else, right? This is all sort of in the same vein, and we'll see how it all ties together once we get to actually solving differential equations in a little bit. But this will be the underlying point from when we know that we've done enough to give us general solutions. It worked for second order, it'll work again for systems in the future.